Eric Barton, Senior Principal Engineer for the High Performance Data Division of Intel. And File System Mater. The Nader, no. Okay. Eric Barton.
Hi. I want to talk today about what we're doing in the Fast Forward project. We first got involved in Fast Forward when we responded to the Exascale storage and I/O RFI when we were still WAMcloud. We put forward, when the proposal came out, we put forward a proposal with partners from the HDF group, EMC, and Cray. And that proposal was accepted by the DOE with some modifications. And then, of course, Intel acquired WAMcloud. And so by the time the project actually started, we renegotiated and expanded the project scope back basically to the original, or practically all of the original scope. Because one of the things we really wanted to demonstrate was that we're not just producing an Exascale I/O stack, but that we'd for HPC, but that it would have application in big data as well. So the partners now include all the original partners and then DDN as well, who are contributing on versioning object storage. So the project is a 2-year project, and the intention is to prototype a complete HPC I/O stack and to learn really from that exercise how to go about building the real thing. It's a phased project. We actually publish all of our work as we deliver the stages of the project, and that's available for everyone to see on our project wiki. The initial project started off with scoping, architecture. We're now in the design phase, and implementation is starting. This will continue for the rest of this year and into the following year with final demonstrations in the middle of 2014. So what are we setting about to do? Well, I/O has always been kind of an afterthought in HPC because everyone has been very obsessed with getting the computing power, and what do we do with our simulation data afterwards has been very much a second-class citizen. And that was okay, really, 20 years ago. But as the importance of defensive I/O has increased, and as the amount of computation available increases the size and complexity of stored data models, it's becoming more and more of a problem. And so what we really want to do is turn the whole thing around and start from the point of view of the application developers, saying, well, what really do applications developers and, most importantly, the scientists who will end up using these storage systems, what are they really going to need? Well, they need to interact with their data in very full and expressive ways. It can't be, you can't consider your data, look at your data through tiny keyholes. You've got to be able to look at the whole thing broadside. And that really means that wherever the data moves around in the system, you've got to be able to either move compute to the data where the data is large and the compute is appropriate for that, or move the data to the compute, onto the Exascale cluster itself. So we want to produce a storage system in which it's the developer, it's the scientist who's really in control of how the data moves around the system and how he interacts with it. We have to overcome today's I/O scaling limits. These data sets are so large, it takes very significant time to move them around. Horizontal scaling issues, like jitter, for example, and excessive locking, is going to get in the way of being able to interact expressively with your data. And of course, fault tolerance is absolutely fundamental. These systems are so large, they have so many components, they are going to fail all the time. And so what we want is a way of ensuring that wherever your data moves, it interacts deterministically with failing hardware and software, so that we have very fast and scalable recovery. Also, there is no such thing as one size fits all. It depends really on your data and how it's going to be used, what sort of redundancy and integrity schemes are going to be appropriate for it. So, we put together some principles behind what would it take, what are the fundamental things that an Exascale I/O stack has to contain. And one of the major issues with horizontal scale, as people are no doubt familiar, is the problem of jitter. When you have strong synchronization between processes, then any sort of scheduling noise, introduced by the operating system, introduced by load imbalance, now with power management being so important, there's another vector for jitter. Any sort of jitter with strongly coupled parallel processing just leads to inefficiency. So it's clear that the I/O system is effectively communicating just like a comms library, and therefore non-blocking APIs for I/O is not only appropriate, it's essential. So the style of API that we've come up with and that we're promoting throughout the I/O stack is one which will be quite familiar to people who know the Portals API. It's one in which you have initiation procedures and then completion events. That can then be applied on many different process models. Secondly, we need the I/O system to act like a single entity. I guess those of you who are familiar with the internals of Lustre will know that actually there's very little coupling between the servers in Lustre. And therefore, for example, when the metadata server decides that a client is misbehaving, all of the object storage servers have to discover that for themselves. And what that can mean then is that a client can be interacting inconsistently with the file system. That has to be fixed. But that's going to involve coupling the servers together. And when we create large clusters of servers, that coupling has to be scalable. Clearly, on the client side, there's an even greater pressure for scalability. But one thing that's different about the client side is that the client has a very capable HPC fabric available to it. And really, the I/O system should be able to exploit that somehow. So what we don't want to do is sacrifice the capability of that fabric by imposing blocking communications, some sort of heavyweight kernel communications library, for example. We want to be able to use the actual communications library the application itself is using. And so on the client side, we've come up with a sort of a paradigm for doing collectives in which we really have a process leader, if you like, that communicates with the storage system and then pushes that information out to its peers by turning whatever it got from the storage system and which is being handled locally into a global handle, distributing that whichever way it wants, and then turning that from a global handle back into a local handle in all of the places that the client actually uses it. So we're using that in a couple of places in the API in order to get scalable client-side communications. Now, one of the fundamental assumptions in Lustre was that we had to have coherent I/O between processes running on different nodes. In other words, it should be possible for one process in one node to write into a file, and for that not to conflict with another process on another node doing a non-overlapping write. Now, that's a laudable aim, and one that we want to preserve, clearly. However, if you entangle that concept with the idea of caching, that you've got to do caching on some sort of block granularity, then what happens is you get false sharing. And so one of the scaling issues in Lustre is that for shared file, clients are having to engage in a locking storm until they've worked out which parts of the file they're actually working on. And then, worse than that, if the individual clients don't align their IOs to the cache alignment, then effectively the clients are communicating through the storage system, pinging data backwards and forwards. So one of the aims of the fast forward stack was really to eliminate locking wherever possible, maybe even entirely. One of the consequences of that is really that it puts the onus on the application in order to coordinate itself and not rely on the underlying storage system. So the way I kind of think of that is that you shouldn't be relying on your storage system for message passing. It's fair enough to use a storage system in order to couple at a very gross scale sort of producer-consumer coupling. For example, a simulation that's outputting time steps and analysis programs that are reading the results of those simulations and performing analysis. That seems fair enough. But once you start doing fine-grained communication through the storage system between processes that are not otherwise coordinated, you're just going to lose performance. So the rule really is that tightly coupled processes should be communicating directly to coordinate amongst themselves and just ensure that the I/O that they do to the storage system is non-conflicting. In that way, we've put the responsibility for serialization where it properly belongs in the application. So the other issue, really, as I mentioned in POSIX, is the fact that the cache is there and imposes a requirement for locking. And really, I think we want to use caches as a way of getting efficient streaming. I mean, a cache is an aggregation device. So you can use it to do small writes and have them aggregated in the cache and efficiently transferred to a server. Similarly, you can use a cache in order to do read-ahead. But if you start trying to use the cache as a way of avoiding reading the same thing n times over, well, now you've given yourself an additional requirement, which once again is going to impose locking. So we shouldn't be trying to really predict the way that the application is going to be using the storage system. Finally, we should have a way of allowing loose coupling between processes, as I mentioned, between, say, a simulation and analysis. But what we don't want that to do is to cause the in-transit analysis program to cause the simulation program to block when it needs to write. So we need a way of enabling concurrency in the producer-consumer case. Now, atomicity. The enormous sizes of data sets precludes any sort of scanning for recovery. So we have to have a storage system which can cope with failures occurring constantly and recover very quickly from them and continue. In fact, we don't want the application to pause at all when there are failures. And so we certainly cannot afford any sort of order n or order system size recovery strategies. Now, that doesn't say that we aren't going to be doing scrubbing, for example. The only way that you can actually protect against bit rot is by crawling over the whole storage system, but you know, on a cycle of days or weeks maybe. So a requirement for the underlying storage system is going to be guaranteeing that the changes an application makes to it are atomic. If the application falls over in the middle of an extended update, then all the half-baked state that it's pushed into the storage system has to be rolled back. So we need some sort of way of describing transactions. And moreover, those transactions cannot block each other. They can't be like what we think of conventionally as database transactions. We mustn't be imposing serialization. But we do want the atomicity guarantees. Another requirement for these transactions is that they must be nestable, because we don't want to impose some sort of low-level transactional model which you can't then layer additional layers in the I/O stack on top of. So we need really the end application, whatever it is, for it to be specifying the transactions that it wants, and then have all of the underlying layers in the stack fit in within that scheme. So the transaction model that we've come up with is one that we've called epoch transactions. And really, think of it this way. All of my transactions have an epoch number. They're totally ordered in time. They're totally ordered in epoch number. What does that mean? Every time I do a transaction, a collection of writes, I label those writes with that epoch number. And when all of the writes for a particular transaction have been committed, then I signal that FAQ with a commit. So now, all of these writes can start heading off to persistence through whatever I/O paths, communications, caches, whatever is on the way between the place that actually initially described the write in the application to the place where the write's going to be persisted in storage. And all of that, during all of that, as the label on the write tells it which epoch, which transaction it belongs to. So we want to allow all of these writes to get unordered, out of, arrive at arbitrary times at the storage device, all of that stuff. If we impose any ordering, if we require any ordering, we're going to be pushing the writes back, we're going to be holding back the stream. So we need to allow total disorder in time, but maintain strict order in transaction number. So that really means that by the time the I/Os get to the storage device, we need some sort of versioning storage server in order to ensure that the writes are all applied in epoch order, and so that what you see when you read from storage is as if all the writes arrived in epoch order. So those were, the preceding slides were some of the principles that went into the design of our stack, and we knew from the beginning that we really wanted a layered I/O stack, so that different layers of the software could address different challenges that occur. So down at the bottom of the stack, we wanted an object I/O model. I mean, somewhat like the Lustre model. I mean, Lustre OSTs are simple horizontally scaled object stores. What gets in the way of using them scalably is the fact that you're layering a POSIX file system over them. So we'd really like applications to be able to access the full scalability of the underlying Lustre object storage model. And so that's, to a large extent, what Deos is. And we're leveraging Lustre itself to implement that. Now, on top of that, we're going to have a transactional, horizontally scaled object model. On top of that, now that you have transactions, you can go and implement a high availability layer. The transactions give you clean semantics for interaction with failing hardware. And now a bunch of different HA schemes could be implemented on top of that, including erasure coding, replication, etc. Now, at this level, we're still dealing with object storage in the way that object storage likes to be interacted with. Now, applications are different. Applications don't really want to have the fact that, these particular objects are stored on disks, and they're going to be, it's going to be many milliseconds, maybe seconds of latency in order to complete transactions against them. These objects are going to be stored in NVRAM. They might be microseconds of latency in committing transactions on them. These objects are really good for streaming I/O. These objects are really good for random I/O. Why do we want to impose worrying about that on the application developer? Today, the application developer has very little clue about how the storage system actually is going to handle his I/O. And one way of looking at that is blaming them for driving the storage system badly. But actually, applications developers are more concerned about doing the science, and that's the way it should be. So how do you cross that gap between applications specifying I/O in the way that they want to, and the storage system being able to offer I/O in the way that it can? And that's where the middle layer comes in, the I/O dispatcher. So the I/O dispatcher, it's really saying, I understand what the underlying storage tiers available to me are and what their properties are. I've received knowledge from the application about how the application wants to describe its objects, how it's going to use its objects. Now I have to make sensible decisions about how I aggregate and stream application objects into storage objects. So that's, on top of the I/O dispatcher, then we imagine there would be a plethora of different application I/O libraries, different ones appropriate to different domains. And the one we've chosen to prototype in the Fast Forward project is HDF5. But object databases, more suitable for other application areas. We really want to encourage a wealth of different libraries at this level. And then on top of all of that are going to be the actual applications themselves, and then the tools for querying and searching and analyzing and interacting with the particular I/O models that applications create. So I'm just going to cover the sort of the sub-projects in Fast Forward. And the first one is about scalable communications on servers. One of the things we've wanted to achieve for a long time is much better responsiveness to failures in Lustre. And the K machine is witness to the fact that the current pinger that's used in Lustre doesn't scale because it's basically every client pings every server, and the result is n-squared communication and congestion and jitter. But if we were to distribute the task of monitoring clients across all of our servers, then actually we'd have the ping traffic would be proportional to the ratio of clients to servers. But what we need then is a way of doing collective communications across the servers in a very fault-tolerant way. So the thing we chose for it is a gossip protocol. Now, unlike something like Chubby or Zookeeper, which achieves fault tolerance by having basically replicas of the root of some communication tree, gossip is a truly distributed protocol in which every process just picks an arbitrary peer in every gossip round to share information with. And almost magically, in sort of log-n rounds of gossip, information from any individual node is broadcast to all the others. So think of it as just a fault-tolerant broadcast. Once you have that, it's very, very efficient in terms of the amount of network resources it needs. It means that we can use gossips to share information, maybe even as frequently as every millisecond across a collection of, say, 10,000 servers. The overhead of that is very small. One message out and one message in from every server on average every millisecond. But what it means with 10,000 servers, after only, pretty well guaranteed less than 16 steps, definitely within a second, you've got global information from all of your peers in a fault-tolerant way. Internally, my sort of personal shorthand for this is calling it the God network, because it is like the hand of God telling you this is what's going on in your cluster. Now, on top of that, we can then overlay tree networks. And we can use those for fault-tolerant, scalable communications across all of the servers. The second sub-project, still on the server side, is a versioning object store. So today's OST requires all of the rights that the application wants. If they conflict, they must be serialized somehow, and that's why we have locking. In a versioning object store, in which rights arrive labeled with the order in which they should be applied, we can persist the rights immediately. It's only when you read them that you actually need to sort out the order in which they arrived, the order in which they should be read. And so our plan there is to use, copy on write as a way of implementing transactions, so that at each epoch we can take a snapshot of the state of the storage target, and then between epochs, writes are just logged on arrival. So those are two of the key subsystems that we're using to implement Deus containers. So Deus containers you can think of really as a partitioned global address space. So think of a file, or a container in this case, no longer as an array of bytes. Yeah? It's got three actual dimensions. One dimension is the shard. So that's the object storage target that this part of the container is going to be stored on. And it's a virtualized thing. It's just addressed by index. Within a particular shard, a container is going to have a flat object address space, just 64 bits of object number. And then each object itself is a byte array. Now, one of the things that's kind of interesting about this, in order to remove completely the requirement for serialization, we just say that an object notionally exists at all time. So this truly is a PGAS in that I can read and write any part of my partitioned global address space. If I haven't written to it before, I'll get zeros. But if I have written to it before, I'll get what I last put there. So that's somewhat different from the way we think about objects today. But what it does is it allows you to implement a truly non-serializing I/O, only labeled by epoch number. Now, upper levels can now use this PGAS to implement whatever schema they see fit. So at the bottom level, we're not making any sort of serialization. All we do is we guarantee atomic transactions. So you've got read and write. You can collect them into transactions, and you've got punch as a way of just storing zeros efficiently. The next layer up, the I/O dispatcher. So this is the layer that is squaring the circle between the I/O that the application wants and the I/O that the underlying storage devices is able to supply. And for Exascale, we're imagining two sorts of storage. One is going to be fast local storage, and an obvious application for that is burst buffer. And the other one is going to be relatively slower global storage. Now, the I/O dispatcher is responsible for managing both of these. It has to support the transactional APIs that we want. It has to do non-blocking I/O, as I described earlier. And it's there to do this rate matching and peak load absorption. It's getting information from the upper layers about how the objects it's passed, the application objects it's passed, are used, and it's using that to make intelligent decisions about how to group these objects together and use the capabilities of the underlying object on the underlying storage in order to get good streaming or place metadata, application metadata on devices that are more suitable for random I/O and high ops, say. It will have an API for control and steering of data, so that, for instance, when a checkpoint is written onto local storage, you can then determine whether that's going to be migrated off to global storage as well. So we're imagining quite an explicit control over how data is migrated around the system here. The top level, or the application library that we're working on in Fast Forward is HDF5. And what we're doing there is we've taken the storage abstraction at the bottom of the HDF5 stack and replaced it with one that knows how to talk to the Fast Forward I/O dispatcher. We're also got extensions in the HDF5 API, again to support non-blocking I/O and transactions. Another important feature that's being added at that level as well is end-to-end data integrity, so that when the HDF5 passes application objects to be persisted to the I/O dispatcher, At that point, integrity information is calculated and stored along with the objects so that when you retrieve them sometime later, we verified that there was no bit rot. And then finally, at the top level, we're demonstrating that the stack we've created is good not just for HPC, but also for big data. And the way we're doing that is we're implementing the GraphLab, an API that can be used in GraphLab, on top of HDF5. So the two parts to the project there, one of them is Ingress, where we're building graphs and describing how they should be partitioned when computation is performed on them, and then the graph computation kernel itself, library itself, where you can do machine learning and graph analytics and so on. So all of this we're aiming to demonstrate. Initial features in the next few months, but the end-to-end stack implementation, a prototype at least, in the middle of next year. What we've learned in doing that, we want to take further. We want to take forward after that, obviously, and production, productize the software, make it stable, integrate it into existing systems, and actually start using it in production. So some of the things we'd like to do, obviously the high availability library of Deos is something that has to be implemented here. We're not doing it in the prototype development itself, since we just don't have the resources to do it. But it's the very first piece of the stack that has to be implemented before we can go into production. And another core piece, really, we're prototyping the stack on ZFS, and to be able to do production in commercial environments, we're going to need a ButterFS versioning object storage device. And then finally, we want to implement a wider variety of top-level application libraries so we can support a much wider set of applications and associated tools. So, any questions?
I think we were planning to hold questions till
All right,
the panel.
absolutely fine, yes.
So let's hear it for Eric Barton.
Thank you.